Hello guys, and welcome back to another video. Today's video is all about the binary search algorithm. We'll kick things off by breaking down what the binary search is all about. Then we'll go through the algorithm together with the help of some examples. After that, we'll jump into implementing binary search in Python. We'll then analyze the time complexity of binary search algorithm, and then we will wrap up by checking out some real-world applications of binary search algorithm. With that, let's get started. Let's start by understanding what the binary search algorithm is. Now, binary search is a searching algorithm that is used to locate a specific value, or rather a target, within a sorted collection such as an array or a list. And take note of the keyword sorted. The array, or rather the list, has to be sorted in either ascending or descending order for binary search algorithm to work, or else the binary search algorithm won't work in such a case. Now, as opposed to linear search algorithm, rather than eliminating one element at a time, binary search algorithm eliminates half of the remaining elements at a time. And the key idea behind binary search is to repeatedly divide the searching space into halves and eliminating half of the remaining elements at each step until the target element has been found. Now, the problem-solving pattern that we are noticing here is what we refer to as the divide and conquer pattern, and we'll see that shortly with the help of an example. Now, let us look at the steps that are involved in implementation of the binary search algorithm, and later on in this video, we will be implementing binary search algorithm using Python. The first step definitely is to create a function that will accept a sorted list and a value, which is actually the target, this value. And then we're going to create a left pointer or a lower pointer to the start of the list, and a right pointer, or rather a higher pointer, to the very end of the list. It doesn't really matter what you're going to call them. And then as long as the left pointer comes before the right pointer, we are going to create a pointer at the middle, which we are going to get using the left pointer plus the right pointer with a floor division of 2, the summation of the left pointer and the right pointer with a floor division of 2. And we will see that shortly. And if this middle pointer points to the wanted value, we return that index, or return true, or return any truthy value, or really take action depending on what our program is trying to do. If the value that is being pointed by this mid pointer is too small, we move the left pointer to where that mid pointer is +1. If the value is too large, we move the right pointer to where that mid pointer is -1. Let us look at this using an example. Now, remember, the precondition is that the array or the list must be sorted in ascending or descending order for binary search algorithm to work. Now, assuming we have this array over here, 2, 5, 6, 8, 12, 22, all the way to 33, and we want to find a value like 12. How do we go about it? Now, going back to our algorithm, the first thing we want to do is to create a function that will accept a sorted list and a value, which we will definitely do. For now, we are interested in the second step, which is to create a left pointer at the start of the list and a right pointer at the very end of the list. And in this case, the lower pointer is going to start at 0, or rather the left pointer. Then the higher pointer, or rather the higher pointer, is going to start at index 8. We are getting this index using this length of list -1, because that is the farthest index. Now, the mid is going to be this low plus high, and then that summation we're going to do a floor division with 2. The value that we're going to get, that is going to be our mid pointer. And then we're going to query this list at mid, and then we see that that particular value is what we're looking for. And you can see we found that element 12, which is existing at index 4. Let's look at another example in our code editor, and let us just walk through that example so that we understand this better. And I'm just going to jump into my code editor so that we go through another example together. We are not yet implementing it. This is just another example that we are going through to better understand how the binary search algorithm works. Now, in my code editor, assuming I have this array over here that is made up of these elements 2, 3, 5, 9, 13, all the way to 33. And assuming I want to find a value inside here, let's assume I want to find this value, let's say this 20 over here. How do I go about it? How do I use binary search in this list over here to locate this value 20? Now, according to our algorithm, we've seen that the first step that we want to do is to create our lower pointer, which is going to start at the very first index of the list, this index 0 over here, and then the higher pointer. So this is going to be my lower pointer. Let me just mark it there. So this is my lower pointer, and then my higher pointer, which is going to be at the very end of the list, or rather the array. So my higher pointer is going to be all the way to the end over here. So this is where my higher pointer is going to be. Now, how do I find this index over here? That is going to be the length of the array minus 1. So the length of this list, or rather this array over here, is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now the length is 10, I'm sorry. So the farthest index over here is going to be 9. So I'm going to place 9 over there. So now I have my lower pointer, or rather my lower pointer, which is 0, and my higher pointer, which is 9. Now I want to find the mid of this low and this high. So I'm going to take this high pointer, which is 9, this low pointer, which is 0, and I'm going to do a float division of that summation with 2. Now 9 plus 0 is 9. So let me just open the Python REPL to find out what 9 with float division of 2 is going to give me. So 9 with a float division of 2 is going to give me a 4. Now, the reason why we are using float division and why we are not using a normal division like this one is because when we use this normal division, we'll get a floating point result, which is not a valid index in our array. Now, if the programming language you're using to implement this binary search doesn't support float division, you can look into the math library of that particular language and look for functions like math and ceil, which are going to give you only this in integer part, even if you're using this normal division. So right now we know that our mid index is 4. And going back to my array, I want to look at where the fourth index is. So 0, 1, 2, 3, 4. So this is where my fourth index is, or rather, this is where my mid is. Now, what I want to do is to ask myself, this value that this mid is pointing, this 13 over here, is it the value that you're looking for? Is this 13 the 20 that you're looking for? And the answer is no. If that is not the case, we ask ourselves, is this 13 greater than this 20, or is it less than this 20? And if it is greater than, if it in our case here, it is less than 20, which means that we are going to move this low pointer to where this mid is plus 1. Now I'm going to move this pointer from this low, I'm going to move it from here all the way to where this current mid is plus 1. So my lower pointer is going to be there. So this is index 5. That was easy to unravel. This is index 5 over here. And now my lower pointer has moved from here all the way to here. Now we now have our new lower pointer and our new higher pointer. Now once again, we add the low and the higher pointer, which is going to be 5 plus 9, and that one is going to give us 14. And 14 with a float division of 2 is going to give us a 7. There is no need for us to calculate it here. Now, 7th index, if this is the 5th index, this is the 6th index, and this is the 7th index. So here being our 7 index, this is our mid. Now we ask ourselves, is this element being pointed at with our current mid pointer greater than or less than the target value, which is 20 over here? So this 26 is greater than 20, which means I'm going to move. Okay, this 26 is greater than 20, and that means that we are going to move this higher pointer to where that mid is minus 1. So we move this higher pointer from there all the way to here. And this is index 6. Now we now have our new higher pointer, which is 6, and our new lower pointer, which is 5. So the condition still holds, because remember, according to the algorithm, we want to continue as long as this left pointer comes before the right pointer. That condition is holding in our example over here, because the low pointer is still coming before the high pointer. So we'll still continue looking for that element. But the moment this low pointer crosses the high pointer, maybe the higher pointer now is at index 6 and the lower pointer is at index 7, then that means that element cannot be found and we should stop immediately. But in our case, we can continue looking for that element because the lower pointer is still coming before the higher pointer. Now, once again, I'm going to add this 5 to this 6, and I'm going to get an 11. And now a floor division of 11 divide by, or rather a floor division of 11 with 2 is going to give me a 5. So the current mid is going to be at this fifth index over here. And we ask ourselves, is this element that is being pointed by the current mid what you're looking for? And the answer is yes. So once we found that particular element, we can return true. We can just take an action depending on what our program is trying to do. Now with that, let us just implement this binary search algorithm using Python. Now, the first thing I'm going to do, according to what we know in our algorithm, we want to first of all create a function that will accept a sorted list and a value. Now, let us just create that function, and I'm going to call my function binary search. This function is going to accept our target value and the list, and we know definitely that that list is supposed to be sorted. Now, the next thing according to our algorithm is that we want to create a left pointer, the start of the list, and a right pointer to the very end of the list. Let us just do that. Our left pointer is going to start at 0, which is the start of the list. Then our right pointer is going to start at the length of this list minus 1. And that one is going to give us the farthest index. If the list has 10 elements, then that means the length of that particular list is 10. Now, the farthest index is going to be 10 minus 1, which is going to be 9. And that is actually going to work. From the basic programming knowledge, you know that the farthest index in any list or any array is given by the length of that particular list or array minus 1. Now back to our algorithm. We now want to keep looping when the left pointer comes before the right pointer. And within that particular loop, you're going to create a pointer in the mid, which is going to be the summation of left and right with a floor division of 2. And if the mid pointer points to the wanted value, we want to return that particular index or return true or take an action depending on what our program is trying to do. And if the value is too small, we want, or if the value that is being pointed by this mid pointer is too small, we want to move the left pointer to mid plus 1. And if it is too large, we want to move it the right pointer where the mid is minus 1. So let us just do right that. And I'm going to keep looping while this left is less than or equal to this right. And in each iteration, I want to find first of all what the mid is, which I'm going to get using this left plus right, and then the summation with a floor division of 2. And if the list, rather if this element at the mid of the list is equal to this target value, then we just want to take the appropriate action. In my case, I'm just going to return true to indicate that that particular value exists. Now, the other case is that if the element that you're looking at, or rather the element that is being pointed, is less than, or rather is greater than the target, if that particular element is greater than the target. So, for example, okay, let us start with the condition if that particular element is less than the target, so that we just be coherent to the algorithm, or rather we be coherent to the example that we had here. Now, if this particular value that we're pointing is less than the target, then we know that our lower pointer is supposed to move to where mid is plus 1. So if this particular element is less than the target, now my left pointer is going to move to where mid is plus 1. And otherwise, if that particular element is greater than the target, if this element that we are looking for is greater than the target, let's say for example when we had this 26, I can't remember well if it was this 26 or 29, but when we had it, you can remember that we had to bring this higher pointer to where that mid was minus 1. So if that particular value is greater than the target, we are going to move the right where the mid is minus 1. Now, with that, we have all it takes to find that particular element if it exists. And once we come out of this loop and we haven't found that particular value, then it means it doesn't exist. And in my case, I'm going to return false, but you can take the appropriate action from your side. So let me call my binary search function over here, binary search. Now my target element is 20, and I'm going to use the same list that we had created up here. So I'm just going to copy that list, and I'm going to paste it here. And since this function is supposed to return something, I'm just going to wrap all of this within a print statement. So I'm looking for this value 20 in this list, and let us just jump into the terminal and see if our algorithm works. Now I'm going to exit the Python REPL and clear my console, and then run Python binary search.py, and when I hit enter, you can see I'm getting true because this 20 actually exists in this list. Now let us try the same for a value that doesn't exist and see if you're going to get a false. So assuming I'm looking for a value like 19, and when I run this and I hit enter, you can see now I'm getting a false because this 19 doesn't exist in the list, which means that our algorithm over here is working as expected. And that really is what binary search algorithm is. Now let us move to let us now understand the big notation of binary search, or rather, let us now study the runtime. Now, the best case scenario is the best case scenario for this binary search is O of 1. You can imagine if we find the target element in the middle of the list on the first comparison, as in the example that we had over here. You can see here we did the first comparison, and in that first comparison, we found our element. So that is O of 1 time, and that is the best case scenario of binary search algorithm. Now, for the average and the worst case, binary search algorithm runs in O of log n. And yeah, so that is all about the big O of binary search algorithm. Now, let us wind up by understanding where binary search is efficient. And we already know this, that binary search will work excellent in sorted arrays or lists. When the array or when that particular array that you have or list is sorted in ascending or descending order, as we have seen, then the assumption is usually that the middle value is the value that is wanted, and that is only possible if that particular array or list is sorted. And binary search algorithm will work very well in dividing the array into halves until it finds that particular element. Another place where binary search algorithm is efficient, or rather where we use binary search algorithm, is in database queries. Now, many databases store data in sorted order based on an index column. For example, the username, ID number, registration number, and all of that. Now, since they are sorted in either ascending or descending order, binary search is usually preferred as the searching algorithm in such cases to find records in such databases. And then last but not least is in file system searches. If you look at your operating system, you will see that your files are by default organized in a sorted manner. So binary search is used to quickly locate a file or a folder within that particular file system. And that's it all about the binary search algorithm. Thank you for staying up to this point, and see you in the next one.